All right, so let's get started. So for lab this week, it's going to be rotational motion. Okay, so again, bring your face shield if you have to face. Then you want to wear the face shield. At least one of you guys. Okay. Um, and then for today's classroom disinfection, Abigail and Sarah. Okay. Um, on Friday, for Friday lab attendees, you guys will come in for the exam 3. Okay, and then Wednesday lab attendees, you guys coming on Monday. Okay, so Monday for the exam. And for those are still in quarantine, you can make up your exam when you are out of quarantine. Okay. Um, so then for Wednesday's lab attendee on Friday, you are going to have the lecture recorded. It's will be online, and then you're going to watch that. Okay. For Friday's group on next Monday, you guys will be watching the recorded lecture by yourself. Okay. Also, for the last 3 homework assignments, they are up online, and then the due dates are also indicated by that. Okay, so for number 10, I think you guys still have enough time, usually like a week of time to finish it. Okay, but for 11 and 12, because we are getting closer to the end, so you guys only get like 2 days each for the assignment. So I figure that's not fair. So then extra credit will be assigned if you finish those 2 assignments. Okay, so each one, if you get 100% correct, then for your final grade, for example, if I having an 80% final grade, then it will be 81. If you did 11, 100%, and then if you did 12, 100%, then it will be 82. Okay, so just add it directly to your final grade. Okay, so for those 2 incentives. Then for the final exam, then the content in those 3 assignments will be covered. Okay, so make sure even if you don't have time to finish 11 or 12, for some of the problems, you still want to study the solutions to see, to make sure you know how to solve the problems there. Okay, all right. So that's what we have for the remainder of the semester. That's the schedule. And then for lab, if you guys are missing labs, there's still chances to make up your labs during next week, Wednesday, Friday, and then the week after next week, the Wednesday afternoon. Okay, so there's still chances for make up labs. All right. So today, I think we should be able to finish chapter 10. So let's start with what we learned last time. Last time we learned angular momentum. So then the definition is similar to what we have in the linear momentum. So angular acceleration, we use L as the symbol equal to moment of inertia, which is the analog to the mass in linear motion, and then times omega is the angular velocity. Okay. And then for a point mass, a point particle, the angular momentum is equal to the R times P, which stands for linear momentum of the object. So it's M times V, okay? Times sine of theta, so which theta will be the angle between R and P or R and V, okay? So because P and V has the same direction, so it'll be that angle theta, okay? And we talk about dynamics of rotational motion. So this is an analog to, again, to Newton's second law, F equal to mass times acceleration. So in this case, then torque equals to moment of inertia times angular acceleration. Okay, so delta L over delta T is the analog to delta P over delta T, okay, which is the force. In this case, it will be the torque, okay. All right, so with that, torque then equals to moment of inertia times angular acceleration, or equals to delta L over delta T. So in the case that if torque is equal to 0, right, then delta L is going to be 0, right? So then there will be no change in delta L. That means angular momentum will be conserved. Similar to when we talk about linear momentum, if force is equal to 0, then momentum is not changed. Okay, it's not changing, so then momentum is conserved. All right, so in this case, so for example, if you look at the scenario over here, if a person is sitting on the stool here that can rotate, okay, If he has two weights on his hands, now he may get a help from a second person to give him an initial spin. So then if as he pulls the arms in, his angular velocity will be increased. Okay, so you guys actually can do this by yourself sometime later. Okay, um, just obtain an initial spin with the arms extended, and then pull your arms to your body. You'll see that your um, velocity will increase, angular velocity. So in this case, the person's body and the two arms, okay, you can treat them as one system. As he pulls his arms in, so then all the interaction, the forces are internal force, right? So then external force will not involve here. So then torque by external force should be zero. So then torque is going to be zero. So then angular momentum conserved. Okay, so that means I initial times omega initial is going to be equal to I final times omega final. Okay, so in this case, when his arms are pulled in, the R for the two arms now are closer to the X rotation. So R for the arms decreases. So then the total moment initial decreases, right? So I final compared to this I initial is smaller. So then omega final will be larger, okay? Because of the angular momentum conservation, all right? So let's take a look on this first example here. So it says an ice skater begins a spin. His angular speed is given as 3.04 radians per second. After pulling in his arms, his angular speed increases to 5.24 radians per second. Find the ratio of the skater's final moment of inertia and his initial moment of inertia. Okay. So as he pulls his arms in, there's no external forces, right? So then the angular momentum should conserve. Now we are going to assuming that the friction force in this case from the ice to the skate are small here, okay? So then tau is equal to 0. So then delta L should be equal to 0, or in that case, final equal to initial, okay? Angular momentum final should equal to initial, all right? And you're looking for moment of inertia final to initial, I F over II, okay? Moment of initial final divided by moment of initial initial there, okay? So if you set up this equation, that means I final omega final equals to I initial omega initial, okay? So then from there, now this is what you are looking for, right? So you want to kind of rearrange the terms so you have this on one side, this expression on one side. So let me pull this guy over here. All right. So you can see you actually can bring II to the left-hand side, right? So then divide both sides by II. So then II disappear on this end. Now divide both hand side by omega F, all right? So then it disappears on the left-hand side. So basically then I final over II is equal to omega initial omega over omega final, okay? So you can take so this is the initial speed, 3.04 radians per second. And then the final speed has increased to 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. 5.24. All right, so that will give you the ratio of 0.580. Okay, so that's on this guy here. All right. Let me know if you have questions on this one. So if not, then we will take a look on a second example on conservation of angular momentum. Okay, so on this one it says there are three children riding on the edge of a merry-go-round. You can treat the merry-go-round as a uniform disk. Okay, so from there you can look up the moment of inertia for the merry-go-round. So from last or maybe a couple lectures before, but for disk moment of inertia is equal to 1/2 mr square. Okay, the mass of it and then times the radius square. It tells you the mass and then the radius, so this should be, you should be able to calculate the moment of inertia of the merry-go-round. Okay, and then it says it's spinning at 20.0 rpm. That stands for revolution per minute. Okay, so that's the one unit for the angular velocity. It says the children have masses of 22.0, 28.0, and 33.0 kilogram. If the child who has a mass of 28.0 kilogram moves to the center of the merry-go-round, what's the new angular velocity in the units of RPM? Okay. So I think I'm going to give you guys a couple minutes to work on this, and then we can take a look at the solution together. Okay. All right, so let's take a look here. So in this problem, you want to treat the children, the three children and the merry-go-round as one system, okay? Um, and in the process that one of the child moves to the center of the merry-go-round, then the interaction will be internal forces, right, between the child, this child, and the merry-go-round, okay? So then the net torque should be equal to 0 on the whole system, okay? So in that case, then you can apply angular momentum conservation, okay? So initial equal to final, which means moment of initial times omega initial equal to moment of initial final times omega final, okay? Now, you're looking for omega final, right? You're given this guy. So then you want to see if you can figure out this and that, right? So let's see. For moment of initial, you have three children are sitting on the edge. Okay, so that's 4 point. You can treat them as point masses. So it's going to be M1 R1 square, which would be the R, right? The radius of the merry-go-round. So that's fine. You can just say R. You don't want to distinguish between R1, R2, and R3. Okay, and then plus M2 R2, it's the same R, plus M3 R3 should be the R. Okay, so this is the moment of inertia for the three children, and then you want to include the merry-go-round. Okay, so 1/2 the mass of it times R squared. Okay, so this is your initial moment of inertia. Okay, so you can actually calculate this guy, right? So because everything you need to know is given here. So you have R squares. Oh, the third one should be also R squared, not to the third. Okay, you have R squares here, 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 and here. Okay, over across. So you can actually single out R squares. Okay, so M1 plus M2 plus M3 plus 1/2 M times R squared. Okay, so you will just add the masses up, 22 plus 28, and then plus 33, plus the 1/2 of the 100 kilograms, okay, times R squared, 1.60 meters square. Okay, so that can be calculated. So that's equal to 340.48. Okay. Now we will have to see if you can figure out the final for the moment of inertia for the system. Okay, so I final, again, you have three children, you have the merry-go-round. So similarly, M1 R squared should remain, right? Plus M2. Now this time, the second child moves to the center of the merry-go-round. So that becomes 0, okay? The R2 becomes 0, so M2 R2 squared. Plus M3 R3 squared, and then plus 1/2 MR squared, okay? So basically, only this guy becomes 0, the rest should remain, okay? So M1 plus M3 plus 1/2 M times R squared, okay? So again, that because this is 0, so that goes away. You are you single out this R squared, so then it will be M1 M3 plus 1/2 M, okay? So M1 will be 22 plus 33 plus 1/2 times 100 times 1.6. All right. So your I final is 268.8. All right. So you can calculate that as well. Now you have this guy, you have this guy, you have this guy. So you should be able to solve for your angular velocity final. Okay. So angular velocity final then equals to, you divide both sides by IF. Okay. So IF there. So then II times omega I divided by IF. Okay. 340.48 times the initial 20 25.0 RPM. You can use the RPM because your final result is asked in also in RPM. Okay, so you can keep that guy. 268.8. Okay, so that will give you your final angular speed of 25.3 RPM. Okay, in revolutions per minute. All right. Okay. Any questions you guys might have? All right. So if you are clear, we can move on here. Um, so I think we have talked about angular momentum conservation. So then the next thing, as we discussed in linear motion, was collisions, right? So then in this case, we'll be talking about rotational collisions. Okay. So in the figure here, on the right here, so this is a typical like a music player. I guess you guys, most of you guys would not have seen this, but this is old fashioned like a DVD player or kind of that. So it has a turntable, then you put a DVD on top. Okay, so the turntable initially will have a angular speed, all right, and then this guy is probably having initial angular speed of 0, and then you just put it on top of it. So then there's collision happens here. So this is an angular or rotational collision, okay, because the object is having rotational motion. Then shortly after the impact, these two will have the same final angular velocity, right? So this is a collision over here. So similar to linear collision, we are going to assume that any external forces here are negligible. So then you can apply conservation of, again, angular momentum here, okay? So whenever you see collision, you can apply that. And then for the lab this week, you are actually the second part of lab, you are going to study the angular rotational collision, okay? All right. So in the previous figure here, you can see you actually have two objects, right? They can be rotating with an axis, right? But sometimes you might have like a point mass that is colliding with a object that can be rotating with an x rotation. So for example, here, if this end is fixed here, but it can rotate with the pivot point at this end, all right? So then if this mass hit on this end, then if they stick together, so then the whole system will be rotating with the angular velocity, right? So then in this case, you are going to calculate what's the angular momentum of this guy, initial angular momentum of this guy, with respect to the x rotation going through this one, right? Because for point mass, you can also calculate the angular momentum of it. Okay, so it will be r times m times v, all right? And then after the collision, if they stick together, then you can treat the two as one system. You can calculate what's the moment of initial with respect to this x rotation, okay? So then this part will be a stick, this part will be point mass, okay? There's this example in the textbook you guys can check, okay, to see how you can actually solve a problem like this, okay? We are going to look at a problem similar to this one. So here it says a student sits at rest on a piano stool that actually can rotate without friction. The moment of initial of the student stool system is 4.1 kilogram times meter square. Okay, should be meter square there. A second student tosses a 1.5 kilogram mass, so you can treat that as a point mass with a speed of 2.7 meters per second to the student on a stool who catches at a distance of 4.40 meters from the X rotation. Okay, what's the resulting angular speed of the student and stool? Okay. So let me make a sketch here to help you guys visualize the problem. Okay. So again, a sketch could be just a very simple sketch. It doesn't have to be very perfect. Okay. So something like that. The stool, the student sitting on that. Okay. So then it will rotate as this. This is the X rotation. All right. Now, this is what initially you would have. So initial omega should be 0, right? Student and stool and sits at rest on the stool. So omega initial is 0. All right. Now there's a point mass being thrown and then caught by this student. So this is the point mass. Okay, M, that's equal to 1.5 kilogram. And then this is caught by the student at this location, which is 0.40 meters. Okay, so that's the R there. Now you can imagine it's going to be somewhere in that direction with the velocity or speed of 2.7 meters per second. Okay. So then after it's caught, then the student's stool and the mass, you can treat them as one system. So student stool plus the mass as one system, right? You can do before and after. So there's impact here, or collision over here, before collision and after collision. So then after collision, the whole system will be rotating in that direction, right? Omega final. Okay, you're looking for the omega final. All right. So if you treat them as one system, then you can apply angular momentum conservation. Okay. So again, I'll have you guys try this, and then we can take a look on the solution together in a few minutes. All right, so I think we can take a look here together now. So as I say, you want to treat the students duo plus the point mass as one system, right? So you can write them moment of initial equal to angular momentum equal to angular momentum final, conservation of angular momentum, right? So that's now this time let's check Li and then Lf separately. So initial angular momentum should be equal to angular momentum initial of the student's duo. Okay, so I'm going to use SS student's duo initial plus angular momentum for the point mass. Okay, L sub m initial. All right. Now for the student and duo initial, that should be 0 because the student sits at rest. Okay, on the stool there. So for the point mass, if you remember, it's going to be RMV, R times M times V. Okay, if R and V are perpendicular to each other. So this time we can assume that they are perpendicular to each other. Okay, in that sense. All right. So then this is just equal to 0.40 meters times 1.5 kilogram times 2.7 meters per second. That's the initial angular momentum. So that's going to be 1.62 kilogram times meter square per second. All right. Now let's take a look what's the angular momentum final. So angular momentum final, after the point mass is being caught, then the whole system will rotate with the angular velocity of final, right? So that should be equal to moment of initial for the student's duo plus the point mass. So I'm going to say I sub SS and M times omega final, right? So we're looking for omega final, and we know this for angular momentum conservation, this guy should be equal to this guy, right? So this is 1.62, and you're looking for this. So you need to find what's this first, right? The moment of inertia for the student's dual and point mass together first. It tells you that moment of inertia for the student's dual, okay, then the whole system moment of inertia should be equal to the student and dual plus the point mass, right? So this guy is the 4.1 kilogram times meter square. And then for the point mass, if you remember, for point mass, moment of inertia should be equal to mr square. Okay, so then it's 4.1 kilogram meter square plus the mass 1.5 kilogram times the r square. Okay, so this then would be equal to 4.34 kilogram times meter square. Okay, so now you have this guy, which is that one. You're looking for omega f. So omega f then equals to LF divided by ISS M. Okay, so 1.62 meters square per second because angular momentum final should equal to angular momentum initial. Okay, divided by 4.34 kilogram times meter square. Right, this will give you 0.37 radians per second as your final angular speed, okay, or angular velocity. All right. Again, you can let me know if you have questions about this one. Okay. I think we have time to take a look on a second example here. So the second example here on the collision, rotational collision, it says two twin skaters approach one another as shown in the figure and lock hands. Okay, so they initially have linear motion, but right after they lock hands, then they will rotate, right? So then after the collision, it's going to be rotational motion. Okay, so you can treat this as the initial before collision, and then this is after collision. Okay, so it says given that each had initial speed of 2.5 meters per second relative to the ice, each has mass of 70.0 kilogram, and each has a center of mass located 0.800 meters from their locked hands. You may approximate the moment of inertia to be that of point masses at this radius. Okay, so use that as to calculate the moment of inertia. Okay, and part B, it asks you to compare the initial kinetic energy and final kinetic energy. Okay, so I think on this one, we can take a look at the solution together. So you want to treat them as one system, right? 2-point mass system. So again, then when they lock hands, so the interaction will be internal interaction. So then net torque will be 0. So again, you can write angular momentum initial is going to be equal to angular momentum final. Okay. All right. Now, initial angular momentum, if you look at the figure in the PowerPoint slide, right? For online folks, you want to check the figure on the PowerPoint slide. So then they are having, you treat them as point masses. So then it will be for initial Li will be R times M times V, okay, for each of them. So then let's see, where's my, so then Li initial, it should be equal to R times M times V, okay, for each of the skater, and then there are two of them, so 2 times that, okay? And that can be calculated. All right, so let me take a look here. All right, so let's just leave it here. Now for the final, or the final angular momentum, okay? When they lock hands, so then it's going to be equal to I for final times omega final, okay? So in this case, then you treat them as point masses, so then I equals to mr squared, okay? And then there are 2 of them, so 2 times that, okay? And so let me see here. Right. So then you can set this to up. So you can say Li equal to Lf. So then 2 times Rmv, that's Li equals to Lf, 2 times mr squared times omega. Okay. So that guy. So this is, you take this in the place of I there. All right. So then in this case, you can see this is what you have. So then 2 and 2 can cancel out. M and M will cancel out. This R will cancel out the square there. Okay. So then you are looking for angular speed. So angular speed should be equal to V over R. Okay. Divide both sides by R there. R there. That gives you your angular speed. Okay. So then it will be 2.5 on this here, 2.5 meters per second divided by 0.800 meters. Okay, that would be the omega. So roughly it's 3.125 radians per second. Okay, that's your angular velocity after the collision or after the lock hands. Okay, so that's A there. And then B is asking you what would be the kinetic energy final. Compare the initial kinetic energy and final kinetic energy. Okay, so then you want to calculate initial kinetic energy and final kinetic energy. So initially they are having linear motion. So it will be just 1/2 mv square, right? And then twin scatter, you want to multiply by 2, okay? So then it's equal to mv square. Final kinetic energy, after they lock hands, they are having rotational motion, right? So then it's going to be 1/2 I omega square, okay? I is the moment of inertia for the whole system, which is that 2 mr square, okay? So then this equal to 1/2 times 2 mr square times omega, okay? Omega in here, you can see is equal to V over R. So you can put that in here, V over R square, okay? So you put square on the V here, square on the R here. So then you can see 1/2 and 2 cancel out. R square and R square cancel out, okay? So then you also end up with mv square, okay? So K initial is mv square, K final is also mv square, okay? So the initial and final kinetic energy are the same, all right? So you can take the numbers here, 70 kilograms times 2.5 meters per second square, okay? So roughly 437.5 joules, okay? That should be the initial, and then should be equal to also final because they are having the same expression, okay? So the two equal to each other, all right? So in that sense, the collision would be elastic collision, right? There's no loss in kinetic energy, okay? All right. I'm going to pause a few seconds to see if anyone online have question, okay? All right. So if not, we are going to move on here. Briefly talk about the last section of this chapter on gyroscopic effect, okay? So we are going to check on a couple demos here first.
When I hold the spinning wheel, nothing crazy happens. But when I flip it, I spin. Look back, and I stop. Flip it, I spin. So the question is, why am I spinning? So I have to force the wheel to turn over. Now Newton's third law says that for every force, there's an equal and opposite force acting as well. So when I force the wheel is applying force equal and opposite onto me, causing me to turn. So the same thing applies when I'm on the ground, but the friction between my shoes and the ground stop me from spinning. So another way to explain what's going on is through conservation of angular momentum. Now, angular momentum is something that tells you how hard it is to either start or stop something from spinning. And it depends on two things. One, how fast it's spinning. We call that the angular frequency. Two, its shape, or what we call the moment of inertia. So this wheel is rotating counterclockwise. Now I'm gonna teach you a trick. So get your right hand, and I want you to curl your fingers in the counterclockwise direction. And you see that your thumb is pointing upwards. We'll call that the positive direction. So see, this wheel has positive angular momentum with a magnitude of L. Angular momentum is conserved. That means that as long as there are no outside forces, the total angular momentum of the system always stays the same. So when you flip this thing over and do the right hand trick, your thumb points down or in the negative direction. So the angular momentum of this wheel is now negative L. So the whole system, me, the turntable, and the wheel starts out at positive L. But when you flip the wheel now has negative L. So the whole system needs to stay at positive L because of conservation of angular momentum. So I need to spin with angular momentum of positive 2L. That's why I spin the other way.
Hey everyone, it's me, Derek, from the channel Veritasium. And I've been following this series by Destin on Smarter every day about helicopters, and gyroscopic precession is just one of those things that still blows my mind as it did Destin's. So I'm here at the University of Sydney, my old stomping grounds. I'm going to borrow some of their lecture dem equipment to hopefully teach you a bit about how gyroscopic precession works. The first thing I need to do is talk about vectors. Because a lot of things in physics are vectors. That means they have direction. So an example would be momentum and force. Those are two examples of some pretty common vectors. So if I have a cart moving along here, it has some momentum in that direction. And if I apply a force to it, I can change its momentum. So for example, if I push it to the right, then its momentum will increase to the right. It all makes a lot of sense. Well, there's a similar statement we could make about rotating bodies, which is that a torque increases the angular momentum of an object in the direction of that torque. So let's try to figure out those terms. If I apply a force down on this side of the wheel, I create a torque. Now, torque is force times the distance from the rotating axis. You could call it R. So torque is the force applied times the radius away from the turning axis. Now, what's the direction of that torque? Well, we actually use a right-hand rule to define this. And so what you do is you put your fingers in the direction of the radius from the turning axis and curl them in the direction of the force, and your thumb points in the direction of the torque. So the torque is actually out this way at 90 degrees to the force. The force is down that way, but the torque vector is actually pointing out this way. So the angular momentum of this wheel is being increased in that direction. So the more I apply this torque, the more I increase the angular momentum of the wheel in the direction of the torque. So I'm making this wheel have a very large angular momentum out towards the camera, out towards you. Now before I go any further, let's have a look at this setup that I've got. I have a wheel here hanging from only one side by this rope. And so right now there's actually a torque on the whole system if I let go, because the weight of this wheel is pulling down, and that force is applied at this distance away from its pivoting point there. So if I let go, well, it does exactly what you'd expect. The wheel swings down this way. But I want to see that as an example of rotational motion. There's a torque which is pointing out this way, which is trying to increase the angular momentum of the system in that direction. Now, angular momentum in that direction requires that the whole system starts swinging anti-clockwise. And so that is what happens. But what happens if I only let go after I've already spun up the bicycle wheel? Well, in that case, the bicycle wheel would already have angular momentum this way, and so a torque pushing that way actually swings this angular momentum round that way. Okay, so let me try to get the wheel spinning and make it work. Come on. Oh, look at that. It's rotating as we predicted. See, the angular momentum vector is pointing out this way, but torque is pushing it this way. So angular momentum, torque, and torque is pushing that angular momentum vector around. Except not for long, because this appears to be a quite frictionful wheel. So check out Destin's other videos.
All right. So I think that explains the first one explains the moment of conservation of angular momentum, and the second one is on the gyroscope effect. So I think we've seen the gyroscope effect very often in daily life. So if you are riding your bicycle, then it's on that, because then if you are going with the angular velocity, then this is the direction of the angular momentum, right? And then if you are tilted slightly to either side, then there will be gravity pulling it down here, but the direction of the torque will be actually in the direction that is in that direction, okay, according to the right-hand rule. So then you are not actually falling down if your wheel is having an angular velocity, right? If it's stationary, then it's easily, if you are tilted slightly, you will fall down, okay? So that's on that. Yeah, I think that's what's talked in the video as well. So you use the right hand rule to determine the direction of the torque. Okay, so the torque will be in that direction. Okay, all right. In that sense, just keep in mind that torque is also a vector quantity. Okay, so I think most of the time in this class we only deal with its magnitude. We are not paying much attention to the direction of the torque. Okay. But and that's it for this chapter. Okay, so we'll stop here for today.